Yes, hello. My name is Tija Sīle. I'm from University of Latvia, from Faculty of Science and Technology. I apologize, I'm a bit sick today, but I hope that will not make my presentation much worse. So the topic of my presentation is how to determine wind speed without measuring it. Of course, the topic is about wind energy, but when I was creating this presentation, I actually answered this question in presentation, but it's pretty far towards the end. So we will get to that question, but before that, we need to start with some introduction. So, why do we need wind energy at all? Because I will start by assumption that renewable energy is good. There can be many different opinions, but I don't think that this is the time and the place to discuss them. So let's assume that renewable energy is good. The thing is that solar energy is much cheaper and easier to install from a regulatory perspective. What has happened with solar energy is that the cost of solar energy, it has decreased rapidly, exponentially. It's, if you know the Moore's law for computers, then it follows the Moore's law, the price of solar energy. Why do we need it? Why do we need wind energy at all? The thing is that we still do not know how to accumulate energy easily on industrial scales, on scales that is relevant for the wind grid. And the solar has quite significant limitations in this regard. As we regrettably know, here in Latvia, during the winter, the sun is a rare occurrence, and it's typically about 1 hour of sunlight per day, if that. And of course, there is no sun during the night. So we need something else. We need wind energy. That is the opposite of solar in terms of when it is generated. We of course know that the solar has a diurnal and seasonal cycle. Maybe the lesser known fact is that the wind also has both diurnal and seasonal cycle. And what we can see here is the in the graph, it's the energy generated in 2023, and here are only two of the sources. The orange is solar and the green is wind, and you can see that, of course, obviously there is much more solar being produced during the summer, but for the wind the relationship is opposite. We have a lot of wind during the winter, and it is during the winter the wind has almost no diurnal cycle. The wind blows almost the same for the whole day and night. But we have this seasonal cycle, and we see that we can complement the solar energy with wind energy. There is one more thing that you need to know about the electricity market, because it's quite easy to, relatively easy, to put on a solar panel. You just buy on this increasingly cheap solar panel. You have a green field with some grass and maybe some sheep on it, and you just install the solar panel in roughly the direction of south, and and you can generate energy. And this seemed like a good idea, therefore a lot of people did it. And now is the situation that when there is a lot of sun in Latvia, then the electricity price is negative because everybody is producing it. So there is a strong economic incentive to generate energy when there is no solar energy. Now, okay, let's assume that we are in agreement that we need some wind energy. The next problem is that the wind turbines are quite high. There are a lot of problems that come together with it, but I will focus on one of them. And the typical height of wind turbine is around 100 meters. I think it's not very surprising that we need to know quite precisely what is the wind speed at 100-meter height. And because the process is so complicated, the wind developers, they need to know the precise wind speed with precision of 5% would be ideal. It's not like in other engineering disciplines where we can just make some safety allowances. The wind needs to be known very, very precisely. And this is very important at the wind turbine height, which is 100 meters. You might think that, well, where is the problem? We have a lot of information about wind speed. The forecast is, I can open my phone and see the wind speed forecast. However, that is the thing that is assumed by default and therefore usually not said out loud. I would say every normal wind speed forecast or wind direction forecast that you see, it corresponds to 10-meter height. It's just by default. You might know that there are lots of wind measurement stations, meteorological stations, around 20 for whole Latvia, operated by our Environmental Geological Meteorological Center. However, they all measure wind speed at roughly 10-meter height. The problem is that wind speed at 100-meter height differs significantly from the wind speed at 10-meter height. Usually, in most situations, the wind speed will be higher at 100 meters than it is at 10 meters. However, I would like to the thing that I would like to stress is that what you see in this graph is that on the x-axis it's wind speed and on the z-axis it's height from the ground. So these are some typical wind speed profiles that we can see. And the important part is that the relationship between the wind speed at higher heights, at the turbine heights, with the relationship of wind speed at 10 meters, there is no one single relationship. If you have measured 10-meter wind speed, you cannot reasonably calculate the wind speed at higher heights, at 100 meters, because the relationship from physical because of physical considerations, it depends on, first, most of all, the land use. It will be different between sea or some kind of urban area, and it also depends on the meteorological conditions. So this difference is governed not only by the surface, but also by the by weather, the amount of sun, the amount of wind speed. So the one conclusion that I would like to for you to take is that if we want to build a wind turbine, we must measure wind at every location where wind turbine is planned, and we must measure it at 100-meter height. That's non-negotiable. You can't calculate your way out of the 10-meter wind measurements. So how can we measure wind? There are two main approaches. One is this cup anemometer, technologically quite simple. The wind blows, these cups go around, and you can determine wind speed. However, again, remember, we must measure it at 100-meter height. So it needs a tower to be put on. And I assume that it's not hard to guess that building such a tower offshore is quite expensive, because you literally need to build a tower in the middle of the sea. There is other approach. You can measure wind speed at quite high at turbine heights from a wind lidar that's put on the ground. it's a remote sensing approach. It gives quite reasonable results, and you don't have to build this tower. You can do it from the ground. However, as we can see, it's not cheap. So, and there are some additional problems. You can't measure wind speed for a day or a week or a month and say, okay, I have established my wind speed. Climatically, it would be good to measure at least 10, 20 years. The definition of climate is the 30-year average, but of course no one has time to do that. But you should try to measure at least 1 year because of the seasonal cycle. And of course, we know that we have hot years and cold years. For instance, we have a very cold summer, a very cold winter right now. We also have windy years and still years. There is some variation between the years. And what we cannot do, we cannot travel in time and say, oh, this is our location. I would like to measure the wind starting from 10 years ago. You just can't do that. So the wind measurement is necessary. However, we need to at least supplement it with something else. And then our wonderful solution is numerical or mathematical modeling, and I will be talking about it for the next slides. So first of all, the numerical modeling or mathematical modeling, it's not scary. It shouldn't be scary. I promise you that you have used products of numerical modeling every day. That's your average. That's your average weather forecast. I would say that all weather forecasts that are not based on the question, you can look at your cat and say that if your cat is becoming fluffier, then it will be cold winter. Those forecasts are not based on numerical weather prediction models, but the rest, I can guarantee you, there has been a model that runs to create this forecast. So what is a numerical model? The simplest way how I can ask you to think about it is that it's a computer program. That's what it is in essence. However, it's a very specific computer program that implements physics equations. Namely, we have found a way, it's quite an old approach, how we can implement physics equations, the laws of physics, in a computer program. And typically, the result of a numerical model is, you can think about as a spreadsheet full of numbers. But these numbers correspond to the values of physical parameters. And typically what we do is we visualize it as a plot or as a map, in most often the case of wind energy. Vladislavs informed me that this will be quite a general audience. So I was thinking, what is the best way how I can explain to you what a numerical model is? And if you are unfamiliar with numerical modeling, I would recommend to think about it as a very precise video game. There are some commonalities that can make you understand numerical models better. And of course, there is also a very interesting thing that you might know, that video cards or graphical processors, they're nowadays very much used in AI and the video cards and GPUs. They started as something for video games, and the underlying mathematics is quite similar, so it makes sense. And we know that the computer programs, they need to know laws of physics to look natural. They are quite tricky to program, and there are two more aspects that I would like to stress. Is that you need that if you want to run a really nice computer game, you need a really powerful computer, and that is very true about numerical weather forecasts. And another thing is that you need the program to work quickly. You need to generate the results quickly. There is no point of video game if you get 1 frame per minute. The same is true for numerical weather prediction models. And I will not attempt to explain the full meaning of computer models. There are university courses for that. But there are 2 things that you need to know about models that I will try to explain to you in a simple way to understand how this wind resource estimation works with models. So the first of all is that this is different from a computer game, that models calculate the evolution of the state of atmosphere over time. And we are simulating a specific time and specific location. Our calculations are, they correspond to a specific time and place. And the other thing is that all models have a property called resolution that determines how precise the model results are. I will go into detail in those aspects over the next slides. So what you have to understand is that models calculate how the state of atmosphere evolves over time. Again, if you would like a more simplified example, we can, let's say we throw a ball in the air. We know the position and the velocity of the ball, and using the laws of physics, we can calculate how the ball will move afterwards. It's the same with weather models. We can we determine the state of atmosphere at a specific time and area, and we use these models to evolve how the atmosphere will change, how a cyclone will come towards us, and how it will start to rain. And what is interesting now, we have to separate 2 different things. One is these forecasts that are on your phone. They correspond to time in the future. The calculation is made so quickly that the forecast is ready before the time has happened. However, what we can do, and what is mostly important for this wind resource estimation, is that we can run the model for a period in the past. We can make the model represent atmosphere in the past. That's one thing. And the other thing is this resolution. Again, very simply put, we divide the atmosphere in very small pieces, both horizontally and vertically. It's called a grid. And almost the general rule is that the smaller the piece, the more precise are the calculations. Again, there's a good explanation why it is the case, but I will not go into the details. And we call this the typical size of the piece, we call resolution. And the typical resolution of numerical weather prediction models are between 3 and 30 kilometers. So now I will be answering the question that I posed at the beginning: how to determine the wind without measuring it. So the thing that is being done by a lot of people is that you run this numerical weather prediction model, you run this computer program, but you put the data in such a way that the state of the atmosphere corresponds to 20 to 30 years in the past for a region of interest. And that's another limitation. Let's say you are interested in a single point. However, the models, you cannot run the model for a single point. It doesn't work that way. Let's say we assume that Latvia is a 500 times 500 kilometers. You need much larger area, at least in the thousands. It's easy to understand if you listen to the weather forecasts, and you know that there is an anti-cyclone over Russia determining the weather today, or there is a cyclone coming from the west. regrettably the whole atmosphere is joined together in processes. And again, getting back to the analogy with computer games, it is computationally very, very, very expensive, and therefore there are only a few institutions that can do that. There are two main types of datasets. That's why I invoke this property of the model called resolution. We have, for example, Era 5, and that covers the whole globe, and it provides wind speed data with 30-kilometer horizontal resolution. However, because of the huge interest from industry in this topic, there are wind atlases with much lower resolutions. For instance, the New European Wind Atlas that I participated in creating it, so I know a bit about it, and it covers only the area of Europe, but it provides much better horizontal resolution. I can go on and on about why small resolution is better, but I want to just point out a few things. A lot of this data is available completely free of charge. And I would like to stress that modeling data is available free of charge. You can just go to one website or another and just download it. And there are also some private companies that are offering proprietary modeling data for a fee, but you almost cannot get high mass these 100-meter wind observations. They are mostly done by private companies, and they are secret. It's a secret information. You cannot get it. However, these free of charge datasets, they can be very large, up to terabytes, and they need to be geo-referenced. They need to have a lot of metadata. So you probably, most likely, won't be able to just download an Excel file. You will need some kind of Python. The data will probably come in specific formats. They're not very hard to work with. They're actually quite reasonable. If you know Python programming, it's reasonably easy to do, but you won't get this data in the normal formats like Excel. And the last point I would like to make: why offshore wind? Offshore wind has obviously its drawbacks, mostly associated with installation costs. However, in Latvia, a simple thing is true, and it holds true quite, almost all situations, is that for Latvian climate, not for Southern Europe, for Latvian climate, there is significantly more wind speed over the sea. This is actually a result of one of these wind atlases that I mentioned earlier. This is the wind power potential over Latvia. Here you can see the color scale. Here, not a lot of wind power. Here, lots of wind power. So it's quite easy. There is, of course, a simple explanation for that. You can think about the wind speed as coming mostly from the west. You have large wind speeds over the ocean, over the North Sea. The wind rubs, and the wind loses its velocity over the land. So we have Scandinavia, a bit where the wind loses its wind speed actually quite a lot. And over the Baltic Sea, the wind is already smaller, and then the wind speed slows even more over the Kurzem. So over the Gulf of Riga, the wind is even slower. That's roughly the case. So I would like to leave some time for questions. So these are just the conclusions, that for wind energy, we need to know wind climate at 100-meter height with quite a lot of precision. We can, of course, measure things, but measurements are expensive and they take a long time. So the alternative is that we can use complicated computer programs to establish historical data speeds. They are, of course, not perfect. You need to compare them with observations, but it has been done for Europe and Latvia. Therefore, I would, if you are interested in this, I would recommend that you start your investigations in this area with those ready-made data sets. So that's all from me. I hope that there will be some questions.
Thank you. I don't know if any questions here. No hands, no responses, and yeah, so no questions from online speakers and listeners as well. It looks very nice, and I recognize Neva map from your last slides. Yes, it's maybe not outdated, but it's not new anymore. So it's like 3 years, 4 years ago, but it's still maybe recent Baltic Sea resource for wind source. It's like wind models. You know, maybe you know about some kind of newest versions or something like this.
The thing is about wind climate that actually, if for temperature and for the number of days with snow, there is quite a significant impact of climate change. Actually, for wind, the impact of climate change is much less pronounced. So the fact that we have older data for older periods of time, it's not as bad as yeah. And the previous European wind atlas, I think, is from the 90s. So there's quite a big gap between these wind atlases. They won't be
for more than 20 years, I think.
Yeah. There is one reanalysis called NORA that it's newer and it's quite good, but it covers I think Latvia a bit. It's mostly focused on the Scandinavia. So there are smaller, more focused products that you can look into, but it strongly depends on the area that you're interested in.
But do you have experience with Copernicus Wind Atlas? As I understand, it's based on satellite data. That looks quite new as well, but I have not deeply go inside. So just find it's nice data, but not able to compare it with NEVA, for example.
I will have to look into that. What I can say that from satellite, first of all, from satellite you can measure the wind speed only over the waters. And also there is this problem that I already talked about, that when you are using satellite, you are measuring wind speed over the water by measuring the properties of the small waves on top of the on top of the water. So by definition, you are measuring wind quite close to the surface of the water. And again, if you want to calculate the wind at 100 meters, then you have to be very, very smart about it. That's the thing.
Yeah, thank you.